We will start with Chapter 3, Standard Linear Regression. In the standard linear regression model, the response y is a continuous measurement variable. We consider linear regression models of the form y equals f of x1 through xk, which is the linear in the k-regressor predictor variables, plus the error term, which is equal to alpha plus beta 1 x1 plus every term through beta k xk plus the error term. Data is collected into the design matrix X, which equals x1 through xk. Error follows a normal distribution with mean 0 and variance of sigma squared. The conditional mean of y given x is f of x, which is alpha plus beta 1 x1 plus beta 2 x2 all through plus beta k xk. The estimation of the parameters is achieved through least squares. The least squares estimates minimize the sum of the squared differences between the observations and the values that are implied by the model. The model is here, which is d equals alpha beta 1 through beta k, which is the summation from I equals 1 through n of yi minus alpha plus beta 1 xi1 plus beta 2 xi2 all through beta k xik with that entire term squared. This is also known as the regression deviance. The fitted value is yi, where alpha hat plus beta 1 hat xi1 plus beta 2 hat xi2 plus through beta k hat xik. And we find the residuals using yi minus yi hat. The term d hat, which is d through alpha hat, beta 1 hat through beta k hat, is the summation from I equals 1 to n of the residual squared, which determines the estimation of the variance of error I, which is the sigma squared, the r squared, and the f statistic. Unbiased estimate of sigma squared is sigma squared of d hat over n minus k minus 1. R squared is found by using 1 minus d hat over the residual squared, and the f statistic is the summation from I equals 1 through n of the residual squared minus d hat over k all over d hat over n minus k minus 1. The large value of f leads us to reject the null, where beta 1 equals beta 2 all through beta k equals 0. Output of regression models provides estimates of the regression coefficients, the standard errors of the estimated coefficients, the summary statistics about the model fit, and the predicted values and prediction intervals for new cases. By adding variables to a model, we are bound to decrease the error sum of the squares d hat and increase r squared. Therefore, the r squared adjusted is found by 1 minus d hat over n minus k minus 1 all over the residual squared minus n minus 1. The k-regressors with k plus 1 estimated coefficients, and this can actually decrease, unlike R. Mallow's CP statistic measures bias. It can be found by using the d hat, a subscript p, minus over n minus k minus 1 times d hat full minus n minus 2 times p plus 1. dp is the error sum with p regressors and the p plus 1 coefficients, while the d full is the error sum of the full regression with all k. This prefers low values and search for very close to p. The quality of the predictions is assessed through the mean error, which should be close to 0, and it indicates bias, and the root mean square error, which expresses the magnitude of the forecast error in the units of the response variable, and the mean absolute percent error, which expresses the error in percentage terms. We want unbiased forecasts with low values of root mean square error and mean absolute percent error. Now we get to the first, which is the estimation in R. The formula below shows us that we can use the linear model to estimate values in R. Now we get to the first example, which is fuel efficiency of automobiles. The data set on fuel efficiencies of 38 cars. We look at the variables that account for gallons per 100 miles, the weight of the car, the cubic displacement, the number of cylinders, horsepower, acceleration, and the engine type. First, we plot the gas per mile versus weight, and we get this plot. Next, we plot the gas per mile versus displacement, and we get the new plot. We check the fuel efficiency and we make it -1. Now we do the regression on all the data. We check the linear model of the regression of the GPM, and we check the summary. This shows R square is 0.9386. And we look at the correlation of every variable. This shows that predictive variables are related through correlation matrix. Next, we calculate the R squares, the adjusted R, and the CP values. The best subset regression in R. We have to get the calculations through the library leaps. This shows that the trade-off between model size and model fit, the model with only weight has the R square of 85.8. When you add displacement and the number of cylinders, this changes to 90.3. Now we check the linear model of GPM versus weight. Now we relate GPM to just weight. We use this for cross-validation. This removes one case from the dataset of n cases, fits the model to the reduced dataset, and then predicts the response of that one case that has been removed from the estimation. We find that the model with all 6 regressors does better. The mean error is -0.004. The root mean square error is 0.35. The mean absolute percent error is 6.75. Now we do the cross-validation of the weight only. The mean error is -0.003. The root mean square error is 0.45. And the mean absolute percent error is 8.23. Now we go to the second example, which is Toyota used car prices. Check the sales prices and the vehicle characteristics of 1,436 used Toyota Corollas. The objective is to predict the sales price of a used automobile. We do not use all the variables. The only variables that we use are price, age, kilometers, fuel type, horsepower, color, transmission, cylinder volume, doors, and weight. First, we check the first 3 rows of Toyota Corolla. Next, we create the indicator variables from the categorical variable, the fuel type with its 3 nominal outcomes, CNG, diesel, and petrol. The objective is to predict the sales price, so we create the scatter plots from the 3 fuel outcomes we checked. First is the plot of price versus age, then the scatter plot of price versus kilometers, and third is the price versus the HP, horsepower. The model explains 86.9% of the variation in price, but we can simplify out variables we do not need, like doors. Now we check the regression on all the data. This is the summary of all of the data. We can see that the R square is 0.8693 and the adjusted R square is 0.8684. The mean error is -4.871. The root mean square error is 1283.1. The mean absolute percent error is 9.21. Now we do the simpler version, which creates a mean error of -2.7, a root mean square error of 1354.5, and a mean absolute percent error of 9.53. You know that a new car is worth more and it depreciates, therefore adding the squares of age and kilometer to the model. We do the first linear model of price versus age plus kilometers, and checking price against age how kilometers has this summary, which pops up with the R squared of 0.79. Now we do the second linear model of age plus the age 2 plus kilometers 2. And this R squared has 0.8335. And finally, we just do the price versus age, H2, and just the kilometers of the first, with an R squared of 0.8322. Now, plot residuals against the fitted models. Scatter plots show that all information is extracted from that model and that some variables are missing. We do the first plot scatter plot of the residuals of the first model. Then we do the histogram of the first model, and then the scatter plot of the second model. The model inadequacies show up in the scatter plot, while unusual cases show up as outliers in the histogram. Finally, we will check the effects of model overfitting in the average mean square error of the regression prediction. Overfitting a regression model increases the variance of the prediction error. The least square estimates of k times 1 vector beta in the linear model y equals x prime beta plus error is given by beta hat, which is x prime x inverse times x prime times y. X is the n times k design matrix. The prediction error for a new case with covariate vector xi has mean 0 and variance of sigma squared times 1 plus xi prime times x prime x inverse times xi. The best prediction with no covariate is 0, and the variance is sigma squared, while the average prediction error variance is sigma squared times 1 plus k over n. This implies that each unneeded covariate increases the average variance by 1 over n. However, the average prediction error variance is increased by k over n.